We'll wrap up Unit 5.3 by doing some example problems so we can finally put into practice a lot of the equations that we've developed throughout these video lessons. So our first question here is to derive a full version of Ampere's law. So Ampere's law is the one that says the integral of B dot ds is equal to mu naught times I enclosed. It's one of Maxwell's equations. That enclosed current could either be a conduction current or a displacement current. So the total current is the sum of both types. So we really need to say that the integral of B dot ds is equal to mu naught conduction current plus mu naught times displacement current. And displacement current, hopefully you recall, is the apparent current that is supposed when you do an experiment to investigate the magnetic field produced by the current. So we know by the right-hand rule, if you point your thumb in the direction of current being conducted in a wire, then you can wrap the fingers of your right hand and you'll see that there's magnetic field pointing out of the page here and magnetic field pointing into the page over here. And if you move the compass down a little bit, you'll still sense that current by the response of the compass, and the magnetic field still points out. Down here where the current is still conducted, you have magnetic field in and magnetic field out of the page. So is there any magnetic field sensed when you put your compass right here? There is, but it's not due to a current being conducted. After all, this is all insulating material, so it's due to that quantity we know as displacement current, which is associated with the rate of change, the growth of the electric field between the plates. So charge is equal to capacitance times voltage, which means it's epsilon naught A over D times ED. The D cancels out, and charge is epsilon naught times A times E. Current is dq dt, so it's d dt of epsilon naught A and E. Well, the area of these plates aren't changing. Certainly epsilon naught isn't changing. So this quantity we're calling the displacement current is equal to epsilon naught times A times the rate of change of the electric field. Of course, we could put the A back into the derivative and say that the displacement current is epsilon naught times d dt of the product of A and E, and the product of A and E is electric flux. So there you have it. Displacement current is epsilon times the rate of change of electric flux. So if we substitute that in place of displacement current here, the full version of Ampere's law is stated as the integral of B dot ds is equal to mu naught multiplied by conduction current plus mu naught times epsilon naught times the rate of change of electric flux. How about some more examples here? If the electric field in the diagram shown to the right points downward, so let's draw that. Some electric field lines that point downward, and they're decreasing in strength. Then what's the displacement current direction? Well, the only way the electric field can decrease in strength is if this positive charge is becoming less and less, which means we're pulling electric charge off of the plate and conduction current must be flowing in this direction. Well, the displacement current is just a sort of extension of the conduction current, so the displacement current will be pointing upwards. So basically, the displacement current doesn't necessarily point in the same direction as the electric field. The displacement current always points in the direction of the rate of change of electric field. And because this electric field is decreasing in time, even though the field lines point down, they have a rate of change that points up. Okay. So we got that one. Next question. If the electric field in this diagram points downward, okay, same sort of deal, and it's decreasing in strength, okay, then the magnitude of the magnetic field at point P is in which direction? So, like we already found, if this electric field is decreasing in strength, it must be because we're conducting electricity off it. The displacement current points in the same direction as the conduction current. So, use the right-hand rule, point your thumb upward in the direction of the displacement current, and you see your fingers point inward, so the magnetic field points into the page. Point P is located 7.5 millimeters from the central axis of the capacitor. So this is referring to the same problem. So this is 7.5 times 10 to the negative third meters. The magnetic field strength is equal to 2.5 times 10 to the negative 8 Teslas. We'll say R equals 7.5 times 10 to the negative third meters. The plates are 4 millimeter by 4 millimeter. What's the value of the displacement current? Okay, well, let's see. In the region near the plates, it's not the conduction current that's responsible for this magnetic field, it's just the displacement current. The integral of B dot ds is equal to mu naught times I, so I is equal to, well, if we choose a Amperian loop in the shape of a circle, then when we integrate all the way around that path, the magnetic field is uniform, and the total loop integral of our path length is just the circumference of a circle. So we have B times 2 pi r is equal to mu naught I. So I is equal to B times 2 pi r divided by mu naught. So we have 2.5 times 10 to the negative 8th times 2 times pi times 7.5 times 10 to the negative third, all divided by 4 pi times 10 to the negative 7th. We can cancel out the pi. Grab a calculator. Let's see what we get. And we get about 1.88 times 10 to the negative third amps, or if you prefer, 1.88 milliamps. Second part of this question, what's the rate of change of electric field? Displacement current is also mu naught, displacement current is epsilon naught times rate of change of flux. So it's epsilon naught times d dt of the product of A and E, or displacement current is epsilon naught times area times dE dt, and that's what this question is asking for. What's the rate of change of electric field? So dE dt is equal to the displacement current divided by epsilon naught and area. So in this case it's 1.88 times 10 to the negative third amps divided by 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared, and the area is 4 times 10 to the negative third meters quantity squared. Those meters are going to get squared and cancel with these. So let's multiply all this out. And we get 1.32 times 10 to the 13th amp newtons per Coulomb squared. Now, is that the same thing as a Newton per Coulomb per second? Well, let's see. An amp is the same thing as coulombs per second. So now we can cancel one of those coulombs, and sure, that's the same thing as newtons per coulomb per second, which is electric field per unit time.